So I think it's more than 2 decades I've been working in this area. So recently in the last 5 years, these are my collaborators, Satoshi, then we have a Russian team, have an India-Russian project going on, and these three are he was my former student, Zodin Mavia, Vivek, and Shashwati is the fresh PhD scholar. So we have been working on this area, understanding more and more deep stuff, and a year and a half ago I got to know what is arborescent knots, so I thought I should put this on the title. Of course, mutants is a debatable area. I know I've had a lot of interaction with the mathematicians about it, but the way we see it from physics and what is the current status, and we keep updating in the knotebook.org all the polynomials. So my plan is I will briefly review how knot invariants are written from Chern-Simons theory, and then we'll get on to arborescent knots. And in the process of obtaining polynomial invariants, we need the quantum Wigner 6J, or these are the Raka coefficients. And once we know this, we could write the colored home-fly polynomials for many of the arborescent knots. And I'll also update what all colors, by color I mean representations, and what knots up to what 10 crossings we have updated. And what is non-arborescent, and it will be taken over by Alexei Slepto, who is here, and on Thursday, right? And then I'll tell you about summarizing and some of the challenging problems we are looking at. Okay, so it's a metric independent theory, and it provides a very natural framework for the study of knots and links. I'm just confining myself to knots here. So this was Witten's 1989, and I've just put in these two mainly because we do try to get various results from twist knots, and these are the lowest in the list of the twist knots. Okay, so every time a physicist starts with a quantum field theory, they start with an action, and this is metric independent. It's a 3 form on a 3 manifold. K is the coupling constant, A's are the gauge connections, and then we look for observables, which are nothing but the Wilson loop operator, which I call it as K, and they carry a color which is the representation of a gauge group G, and this is taken over the curve which is defined by the knot K in 3-dimensional manifold, and we are taking the 3 manifold to be a 3-sphere. And this normalization is technically the partition function or related to the WRT 3 manifold invariants, and these are the quantities which we call it as a knot invariant. So G is the gauge group, R is the representation, K is the knot, and the expectation value of the Wilson loop operator gives you the knot invariants, and we would like to understand these knot invariants. One of the main motivation with which I started 2 decades ago was that how to classify the knots by explicitly computing the polynomial form. So just to give you a flavor of how the knot invariant computation goes, you need 2 ingredients. One is the relation of Chern-Simons to the 2-dimensional boundary special conformal field theory called the Vesuvino conformal field theory. Second is every knot you should be able to either draw it as a closure of braid or also as a quasi-plait or plait of a braid. So these are due to Alexander theorem and Birman's theorem. And for example, the trefoil, you could try to view this in Chern-Simons theory in S3 as if gluing 2 3 balls with oppositely oriented S2 boundaries. And to each of these boundaries, if you see for this particular example, there are 4 punctures, and you can associate a state in the Vesuvino conformal field theory, and the 3 just to signify that we are doing 3 exchanges on this boundary to achieve the state in the bulk, and this is in the oppositely oriented boundary, and we choose it to be the dual state corresponding to that. So once we have this, we can go to a right basis and expand these states in a suitable basis. Typically we take a suitable basis where the exchange operator, which is the monodromy or braiding operator, which exchanges the punctures, we take them to be the eigenbasis of this B operator, and you can expand psi 0 in terms of this basis. And we know that two consecutive braiding between the strand 1, strand 2 do not commute with strand 2 or strand 3. So these two are the famous, we call it as an S and T channel in physics language, but these two are related by a fusion matrix or a duality matrix, and it keeps track of the three representation, all the four representation, and what is the composition. So T will be an element of R1 cross R2 intersection of this conjugate of this representation, and similarly S is used, this basis is what you would use if you want to exchange between the middle two strands. This is what we will use if I want to do the exchange of the punctures on the side two strands. Okay. Interestingly, we find that this duality matrix, all the properties when we study not equivalence and so on, they are exactly like the identities, like the pentagon identity, orthogonality identities of the Raka matrix or the Wigner-6J symbol. So that's the way the quantum version of the Wigner-6J symbol starts showing up in our computation. And this is the main theme, that if we find this for any arbitrary R1, R2, R3, R4, we have a complete solution to our Chern-Simons with SUN gauge group. This is still an open question. So for knots, both the representations in this diagram, even though I have taken it this way, so if I am going to confine myself to knot, all of them will have, all the strands will have the same representations. So I can confine myself to putting all the Ri's to be R. So if I do that, at any boundary, two of them will be ingoing and two of them will be outgoing. So for SUN representations, two of the representation will be denoted as R, and the other two will be the conjugate representation. And this depends on the orientation, as I said, ingoing or outgoing. So formally you could write the state in the basis where, since I want to do the exchange of the punctures in the middle two punctures, I can use the state which is here, which I am denoting it compactly as phi hat of S, and I could write the state in this form with a coefficient mu S, and not equivalences will fix the coefficient mu S to be the dimension of that representation S, which is what is the unknot normalization. So similarly, we could write, as I said, the knot invariant is an inner product of psi 3 with psi 0. So psi 3 could be written as this braiding, which is the exchange of the punctures on the boundary 3 times, and you could, since it's in the eigenbasis, it will pull out an eigenvalue 3 times. All these knot invariants in general will be frame dependent. If you want to work in a canonical framing or standard framing to compare with Jones home fly, which corresponds to R being fundamental, we will choose a frame which is the standard framing or canonical framing eigenvalue. So there is a frame correction put in this with this eigenvalue, and we will substitute it here. Okay, and the plus sign is because the two strands on which you do the exchange of the punctures are parallelly oriented. So there could be situations like this figure 8 knot where some of the strands could be anti-parallelly oriented. So if I am doing the exchange between punctures which involves anti-parallel orientation, then I denote it with a minus sign, and the frame correction takes care of it, and this is the eigenvalue we choose. So the same prescription which I did in the case of trefoil, where there was only exchange between the two strands in the middle two punctures, here you can see that first you have the exchange between the middle two punctures and then exchange between the side two punctures, and you need to do it by going from one basis to another by this Wigner's 6J or Raka matrix, and the coefficients mu s and mu t will be showing up here. So it's a very straightforward exercise of writing any, even though I've done this for a quasi-plat of 4 strand braid, you could do it for any number of strands. Okay. So this method is very, very systematic, and you can extend this in writing the invariant formally for any quasi-plat of n strand braid. So what is the sum total of what I have said here? The knot invariance which you obtain here involves braiding eigenvalues, and the braiding eigenvalues are known. It just determines the quadratic Casimir of the representations involved. So that is known to us, but it also involves these fusion matrices. And what data we have for the fusion matrices? Fusion matrices, we have the result only for SU2 completely. So you could write the polynomial form for any knot, in fact any link, and that gives you the colored Jones polynomial. So that's a complete solution available in Chern-Simons theory. But unfortunately for SUN, such a data is not available so far, and it's still an open question. But using knot equivalences and properties of this Wigner's 6J for low dimensional colors, low dimensional representations, we managed to find the Raka matrix. So once we had this result, for those colors we could write the colored invariants for SUN gauge group. Okay, so those are called the colored home fly, where the rank of the group q to the power of n will be playing like the second variable. Similar story, if you put instead of the gauge group as SUN, I could do it with SON. Even there only for some colors we have been able to achieve. So for fundamental or the defining representation, it will be like Kaufman. For higher dimensional representation, it is like colored Kaufman. Okay. So since we know the colored Jones for 3-1 and 4-1, interestingly Habiro, he was able to get a neat form, using cyclotomic expansion. He wrote this form, and this kind of gave an idea to Mosbaum 2003 to write a nice scheme theoretic relation and determine the colored Jones for a class of knots which is twist knots. So twist knots, if you see here, if you put p equal to -1, p is full twist, then that corresponds to your figure 8, this one which I discussed. And in general you could have p going from -1 to +4, and in the Rolfsen table these are the knots which it corresponds to. So what he did is looking at these two, rewriting it as a double summation for p positive and p negative, and then he could get a neat form for the arbitrary twist knots with p full twists. So we wanted to do a similar exercise with superpolynomials, and superpolynomials was known or refined Chern-Simons knot invariant for trefoil was known for the trefoil we knew, and also we knew for the figure 8. We wanted to do a similar exercise, and we did manage to conjecture a form for the superpolynomial for any symmetric. This is symmetric representation, rank and symmetric representation. So we could get a nice expression, and various checks were done, special polynomial limits, going to the colored Jones limit, all these checks, and the differential method. For all these checks it went through. So it's still, we call it as a conjecture. So the twist polynomial results, we had the superpolynomial from which we could get what is the colored home fly. So once we had this colored home fly, we have a general formula for the figure 8, whatever I wrote in the beginning. I had to only replace this by 2p. I had to replace this by 2p. If I do that, I have a whole lot of equations and I could solve that and determine this matrix. So this is what we tried to do, and we wrote it till up till 4 or 5 boxes, what should be this answer, and then we conjectured a form for the Raka matrix. Okay. So this is one thing which we feel it's a very important contribution. Now any symmetric Rankine invariant can be computed for many knots because we have given this data. Okay. So this gave more data leading to conjecture a closed form expression similar to Kirillov-Reshtikin in finding the Wigner 6J symbol, and this appeared in 2013. So just to give you a flavor, the box with the hard dot means it's an antisymmetric. This is the diagram. So if I put a box with the hard dot, this is equivalent to n minus 1 boxes. So this is the antisymmetric rank. It's a conjugate to the fundamental. So if you have fundamental, then the conjugate is denoted by hard dot on a box. So as I said, 2 of the representations will be R and the other 2 will be oppositely oriented, so it should be R bar. So that's the convention, and when you compose them, these are the following possibilities. So we could write it for, this is one possibility where the 2 side strands are parallel, and you could, anti-parallel, and here the 2 side strands are parallel. So these 2 cases we could get a almost the same form as what Kirillov-Reshtikin had, because all the representations of SU2 will appear as representations of SUN, for at least for the symmetric representation. So for the symmetric representations, all of these factors are exactly similar. If I put capital N to be 2, we get back the SU2 Kirillov-Reshtikin result. The only thing is that we kept an unknown CZ here, which we fitted by looking at the boxes up to 5 boxes, because the twist knot results were available. And after we found that, we could actually fix what is the CZ as well. Okay. So these expressions are written in terms of highest weights and these roots alpha 1 and alpha n minus 1, and it's just an inner product of them. So the deltas also has the same meaning. So these CZs are dependent on the K1 and K2 in a neat fashion, and this we looked at up to 5 boxes and fixed the expression, and for 6 box we checked that it is matching with the twist knot invariance.
What are C-min and C-max?
Yeah, so depending on which one is the, there will be a summation here which is going from one minimum value to the maximum value. This summation is depends on which Q numbers, it should never become negative. So that will put out a window like mod J1 minus J2 to J1 plus J2. So that window will define for you what is an integer which is Z min and Z max. So it's a finite sum. It is not going to be an infinite sum, and we could get the coefficients for the type 1 and type 2. Type 1 is when the side 2 strands are anti-parallel, and type 2 is when side 2 strands are parallel. Okay, so what is the, so once we had this, these are the whole lot of invariants which we could straight away write. N colored symmetric, N colored home fly, we could write for knots drawn as quasi-platter 4-strand braids using the state. But knots out of 4-strand braid is not the only knots we have. We have many more knots with more than 4 strands. So our data is not sufficient to write polynomials for quasi-plat which involves more than 4 strands. For this I need to look at 6 point, try to find the Wigner-6J symbols for them. So that's a very tedious exercise. But interestingly, you could draw every knot. This is what I thought 2 years ago, that every knot I'll be in a position to redraw, like 1071 for example, I could redraw it as a 4 punctured boundary. So each of these are like 3 balls with 3 S2 boundaries, each one having 4 punctures. I could glue them in a way that any knot I should be able to do this, and I will essentially work with a 4 punctured S2 boundary for which I know the state and I know how to write the Wigner-6J symbol. So this was the motivation, and this 10152 is for completeness. I have shown it here. And you need only building blocks, like this is like arbitrary braid word going from one boundary to another boundary. This is a single boundary. You could have 3 boundaries, you could have all boundaries. Each one has only 4 punctures. And you need a state for this R boundaries, each one with 4 punctures, and that also you can write it here, where T is the representation involving product of representations of the 2 punctures. So this is as neat as it can be, and the state will be involving the R boundary state. So once I confine myself to redrawing every knot involving these building blocks, then I can compute many more knot invariants with the knowledge of the Raka coefficients which we have. So like for example, if I want to look at the state, I can redraw the state by looking at it as braiding in the middle strand, put this 3 boundary state and so on. We can systematically go from one to the other in this fashion. So states of this type, states of this type, all of them can be computed. So arborescent knots by definition are knots which can be obtained by gluing such building blocks involving 4 punctured many S2 boundaries. So that's the definition of the arborescent knots. Okay, and I was under the impression that all knots can be drawn this way, but later on with my collaborators I got to know that there's a paper in Russian which talks about that not all knots can be drawn this way. Those which can be drawn are called arborescent knots. So that I got to know only 1.5 years ago.
So which is the simplest one which is not arborescent?
Yeah, I have I think 817 is not, up to 7 crossings everything is arborescent. In fact 817 I think we struggled a lot to draw. We were not able to draw. And then I kept saying maybe we are not able to draw because we are not doing all possibilities correctly, but then they brought to our notice that it is not. Okay, so it's very nice to see that they have nice theorems to show that which one will fall into, but unfortunately it's in Russian, so I'm believing that our struggle in not finding it is actually reflected there in that list. Okay, so just to show you the way we called in one of our recent papers, this each piece, we called it like a finger, and this is actually a pretzel knot, and you can treat it like a 3 boundary, gluing with each of these fingers is like a 1 boundary. And compactly you can even draw this by putting a vertex, and here you put some numbers which will correspond to the side strand crossing, middle strand crossing. So you can compactly denote each of these diagrams by putting L, M, N, and we can use N for the 3rd and 4th, L for the middle 2, and M for the side 2, 1 and 2. So we can use a notation and we can draw, for this particular diagram the integers are denoted here, but we can put it in a way which looks beautiful. In fact, it looks like a field theory Feynman diagram. So this is like a propagator connecting 2 vertex and so on. So you could go further and M2, as I said, is in middle, N2 is in the side, and we can follow a notation and start drawing. There is a 4 vertex, 3 vertex. So this is, we call all those nodes as fat graphs initially, and now we call it as arborescent because we know this term. Okay. So also there is one interesting, in the computation side, we wanted to write one universal graph like this, and if you put different integers, it corresponds to different nodes, and we wanted to maximize the computation. Like in one algorithm, we can get all the not invariants was one of the reason why we picked this up, and the maximal one was involving 7 such parameters, like these crossing numbers, 7 of them we needed to involve, and in that up to 10 crossing, I think there is probably some 200 nodes, let's say, or more. So in that these were missing. We were not able to put it in one universal formula, but most of them fitted in, but all of them were arborescent. Okay, so so far I have given you a flavor of what is arborescent nodes, how the prescription of writing not invariants, and we could work out the not invariants for symmetric colored representations. So mutation as a circle region, you could do a rotation about an axis, y-axis, and these two are mutant pairs. That's the mutation operation. So famous mutant pair starts from the 11 crossing. This is the Kinoshita, Terasaka and Conway nodes. What we see is that if you put symmetric representations of the symmetric colors, this mutation can be composed involving braiding operations as a braid word, and it will be seen as an identity operation. So this is the identity operation as far as symmetric colors are concerned. So this knot and this knot are actually inequivalent, they are not isotopic, but I don't see this operation. I get the same polynomial for this as well as for this with the symmetric colors. So what do we have to do? If you want to detect mutation, we need to go beyond symmetric representation. That is one. And Hugh Martin has papers where he talks about 2,1 representations and so on. But interestingly, in 2014, Ju and Jokers had a very neat way of explicitly going through rigorous way of determining the Wigner 6J for the 2,1. Okay. Yeah.
This 2,1
is
are these parallel oriented strands, or are these is one of them anti? What is the representation 2,1?
Yeah. So this is like the diagram is 2 boxes in the first row and single box in this.
Okay.
That's it.
But it's parallel, not anti-parallel.
No, we don't put a composite. We put a representation as such.
Yeah. Okay.
So the representation which we put on the strands is this. Okay. So what we wanted to do as a curiosity exercise, because this mutant has been nagging me for the last 2 decades, I have not been able to find the invariant which can distinguish both of them. So the first exercise we wanted to do is use their data, and since we could draw this as a fat graph or the arborescent knot, we thought we should work out the 2 uncolored home fly for it explicitly. So this was achieved. We wrote this polynomial for the Kinoshita, Terasaka and Conway explicitly, and we found that the difference is also not 0. So this gave us a very explicit verification, even though Hugh Martin has said that the difference is non-zero for 2 uncolored in the quantum group invariant for n equal to 4, rank n equal to 4. We did this for any arbitrary SUN representation. So and this evaluation is not difficult, it's just a straightforward exercise for us. We needed only this data of the Wigner 6J which we got from 2014 paper. So one of the crucial input which goes in this context is multiplicity. So what is multiplicity? If you take a representation R and compose it with R if it is parallelly oriented, all these representations are appearing only once. The colored in red is appearing twice. I am giving an additional index to it, 0 and 1. Okay. So this is the additional input which comes in when you have representations with whose tensor product can have more than once the same representation to appear. And this multiplicity plays a very crucial role. So once we have this, so we put in an index, multiplicity index Ri. So whenever we draw this 4-point conformal block, so this is R bar, and typically I have a T here. I need to introduce one more index R1 at this point and R2 at this point, which I didn't need to do when it was multiplicity free, but now I will write this representation T colon R1 comma R2. So that is the modification we need to do. The state's 4-point conformal block not only has a representation, but I have to decide what is which representation. Is it this or is it this? And similarly on the right hand side. Both can be different. The product can be giving us a singlet. Both can be different in the sense the Young diagram is same, but these two could have some tag on the braiding eigenvalues which I will put a sign and change. So that freedom I have. Of course, this evaluation of many of these quasi-flat 4-strand was done by Ju and Jokers using this prescription. The only thing is for arborescent knots with more than 3 boundaries, we extended it because we needed that to the computation of mutants. Okay, so just to give you a flavor of this is something when the paper went on review, I saw the referee had written very neatly how you could represent it, so I thought once I presented it, I also wanted it to be in the seminar in that fashion. So I let me just go over the way in which the presentation looks neat to see how to detect mutation even for an arbitrary 2-tangle. So any 2-tangle F, you could write it as a state. This I have already done for trefoil and figure 8. So you could rewrite this as in a state in a 4-punctured S2 boundary. Similarly, if you do a mutation operation, rotation by 180 degrees about y-axis on a state F, it goes to this, and that state will have a different coefficient. Okay, but you know that my on the state should give me this. My is a set of braiding operation which I have to do on this. So if I do the set of braiding operation on this, I know how each one will give you eigenvalues and so on. So if I do that exercise, I do find that the F tilde is related to F up to a sign. See, if R1 and R2 are same, then I will not pick up any sign, which also tells you that for symmetric representation, this F and F tilde will be the same. It's an identity object. But if you have multiplicity, then F tilde is in general not same for at least for the representations which has the multiplicity index, the red colored representation which I had here. Okay, and you can show that F tilde will be related. So once I have this, if I want to see whether this invariant is detecting mutation or not, I could just do the difference. I don't need to do the complete invariant evaluation. For completeness, yes, invariant for Kinoshita knot is this, invariant for Conway is this, but to detect mutation, it's nicer to just do the difference. And it even takes a very short time in the program to find the difference, because it has to only look at the subspace where there is multiplicity. Others don't contribute. So this difference can be formally written in terms of these coefficients. fact, in this particular example, it was involving anti-parallel, so I have put the representation which has that multiplicity index. And you need to cap with the G tangle and to get the mutant pair, difference between the mutant pairs. So that is what we did, and formally this is the index. Okay. There could be some mutants, there are some mutants in fact, where these coefficients turn out to be 0. So still there are mutants which are not distinguished. So we have not still done this complete classification. Even in 11 crossing mutants, there are some mutants where this could be trivially 0 and you don't get any answer. Okay. So at least for the Kinoshita and Conway, this coefficient was non-zero and we could find the result. So just to show in the Kinoshita, this is what was that circled region which I showed in the mutant slide, this one. This one is drawn here, and that's the F tangle, which I, by not, you are allowed to pull and push, you could draw it like a 4 punctured S2 boundary, and the G tangle will be redrawn this way. So once I have this, each of these states I know how to compute, which is what we wrote. The GT coefficients are this. Now all these Rackham matrices will have R1, R2, R3, there will be 2 indices for this state, 2 indices for that state, so you will have 4 indices with them. So it's a straightforward exercise that we could work out the mutant invariant, and we could also work out the difference. Okay. So what is the non-arborescent knots? So we have 2 types of knots, those which can be drawn with boundaries with 3 or more S2 boundaries, each one with 4 punctures. Those knots are what we call it arborescent, and we need only 4-point conformal boundaries to determine the knot invariance. Times we call this as a double fat diagram. There are other knots, as I said, like 818, sorry, it's not 817, it's 818, which we couldn't draw. And in the 9 crossing, you can see 934, 939, 941, 47, 49. And in the 10 crossing, 100 to 123, and 155 to 165. So these are still up to 10 crossing. There are so many knots for which we cannot evaluate using our method, even the symmetric representation. So interestingly, there are, parallel papers where Alexis Lepto and collaborators, they have worked out by highest weight methods, inclusive Rackham matrices and so on, which we will be talking about, where they could compute. The methodology of computing for closure of any 3-strand braid is very simple. They could get answers for them, and in that process some of the arborescent also they could compute as a verification. So both the methods complement each other, and in the process the whole set up to 10 crossings we have been able to achieve. So that's something which is very interesting, that up to 10 crossings all symmetric representations can be worked out, not all symmetric, I should say, by this method up to 4 symmetric has been done. So we have been able to make progress year after year in updating all the polynomials for colored home fly, and so stay tuned for Alexis Lepto for the non-arborescent part. So conclusions, to summarize, I have told you how n-colored home fly polynomials can be computed, and for mixed representations, this is one of the challenging questions. For arbitrary representations, whether we can find the Rackham matrix is not clear. At least case by case, can we get some idea, or is it very tedious to find? One of the reasons why we need this is, especially there are some mutants which I think can be detected if there are more than 3 multiplicities in the tensor product of representations, and Hugh Morton says that you need a representation like 4, 2, and to do that, to do explicit verification, for some of these mutants which are like anti-parallel pretzel and so on, we really need data on the Raka matrix for mixed representations. We don't have it right now, but we hope we will get some more ideas and insights from our computation to get some information. Right now, we think we are very close, at least for the rectangular representations. So this is what I call it as n comma n. We could find the Raka matrix is what we think, but still I think we need to do a lot of tests and see whether we have a way of understanding that. The advantage with that is that it's still multiplicity free. It is tensor products of representations of this type will again be multiplicity free. So at least multiplicity free, why only this? You could have m number of rows also. That will also be a multiplicity free. So we should be able to aim for getting at least those colored home flag polynomials. So that's still a challenging question which we think we are very close, we are trying. And just to update, all our data is periodically updated in notebook.org, involves students, postdocs from ITEP group and from IIT Bombay. And so far we have up to colors which involves 4 boxes. So this 4 boxes involves mixed also. The mixed computations are done by the other method, 3, 1, 2, 2 and all. So we have data for all knots, both arborescent and non-arborescent, up to 10 crossings. So I stop here and take questions. Thank you. Yeah.
Are these, I'm not sure if this is a question to you or to the audience, but are these arborescent knots special for some other reason? If you consider some other properties, whatever, some invariants, homologies.
Take their branch double coverage to get graph manifolds.
What manifolds?
Graph manifolds.
Graph
Things
manifolds.
that are cycle type pieces stuck along the top.
Is there some way to detect if a knot is arborescent, like quicker than trying to draw the diagram?
But I mean, well, you could take a double branch cover and ask whether.
Okay. Yeah, but is there a way out to, if I give you a knot, can we say it is arborescent or not arborescent? I don't know. Please, I don't have an idea on that.
However, could one try to use this to get some condition? Is there
I
something
think-
special that comes out about your formula that somehow makes it different than the generic colored Humphrey polynomial? Because it has this presentation.
Yes. So,
Well, then that's it.
no, but what I'm saying
Be
is,
able to compute that.
first to redraw the diagram as a fat graph, mostly we'll be able to do it. If we struggle, then we know more or less it is non-arborescent, but that's not a rigorous proof, I agree.
No, but I'm searching for a property of the n-colored Humphrey that can detect.
Oh, that I'm not sure. You are asking whether there is a property in the colored home fly which could tell me that.
Yes, and it should follow from the way that you have represented the knot in terms of this very specific way of breaking free space. A special property that it has because it can be obtained this way.
It's definitely a different method, but looking at the polynomial, I don't know whether I can extract that out. That information is not clear to me.
Okay, what about Covano homology, please?
I know no good statements about the
For non-arborescent.
This is also going to be a question for the audience, but I mean, if people try to compute super polynomials for arborescent knots, and like color, for color homology, I mean, you sort of started with a twist knot.
See, the thing is, this is something which I tried, the method which I wrote, I wanted to write a refined duality matrix. And the refined braiding matrix is the T matrix which is available. But the refined duality matrix is not really related to some deformation of McDonald polynomials. So unfortunately, I tried from the StatMech model of writing the R matrix, finding two parameter deformation. So as he says, no deformation and the refinement, now I'm really confused. So there should be some deformed R matrix or refined duality matrix which will help me to write my invariant formally. That is not happening, even for SU2. Forget about SUN. So that is something which if it happens, then you know, but it's not expected is what someone was saying. It's not expected. Yeah, you had something to say.
No, it just sounded like refined transcendence techniques would only work for non-various issues.
That's right.
The arborescent ones are very general.
Yeah. No, but the invariants which I write formally, I could try to use a deformation of the existing quantum Bracca matrix. But I was not able to do it. Even for figure 8, I was not able to reproduce the Kono invariant. So in that sense, it looked like it is more than combinatorial if you want to do Kono invariant.
Any other questions?
Okay, thank you.